So thanks a lot. I really would like to thank for this invitation. I heard this morning really interesting talk, and I hope to give my contribution to the discussion on this matter. So as you said this talk is about this probability law, which is called Benford law, and that can be used to detect fraud. In particular, with two colleagues, Raffaella Coppier and Elisabetta Michetti, we are trying to see if it is possible to use this law to discover tax evasion in Italy. So this is the structure of the presentation. I will start by introducing the Benford law because I was said that the audience was quite heterogeneous, so it could be well known to some of us, but not to the others. So I apologize with the statistical colleagues for some stuff that they already well known. And the second part will be about the use of Benford's law in fraud detection. And the very last part will be on some preliminary results from what we are trying to do. That is, as I said, trying to use this law to see if it's possible to help in detecting tax evasion from firms in Italy. So I will start with some empirical examples because this law was actually originated from empirical observation of quite surprising fact. The fact that in many real sets of numerical data, the leading digit is likely to be small. What we mean by leading digit, the leading digit is the first from the left non-zero digit in a number. So here you have a few examples. If we have the number 23, the first leading digit is 2, in 0.31 is 3, and in minus 1.5 is 1. So here I'm considering three different sets of data. These data are about countries all over the world and concerns the population of these countries, their area in square kilometers, and their GDP per capita. So separately for this data, we are going to see what is the leading digit, and we are going to count how many times each digit occurs. So for example, how many times we observe 1 as first digit, how many times we observe 2, and so on, up to how many times we observe 9 as first digit. And we might expect that all digits have the same probability of occurring, of being observed. So we might expect to observe nearly the same number of times 1, as well as 2, 3, or whatever till 9. But actually, this is not the case. So in this figure, you have the distribution separately for the 3 data set of the first leading digit. And what we can see in all of them is that the number of times that we observe 1 as first digit is much larger than the number of times that we observe any other digit. So we have nearly around 30% of time we observe 1 as first digit. We observe 2 around 20% of time, and then as the digit increases, the number of occurrences decreases. So the relative frequency of times we observe the digit decreases. And this is true, as I said, for all the 3 data sets. And these proportions are quite stable in the 3 data sets. And similar things can be observed on plenty of real data coming from plenty of different fields. So this observation led to the development of this probability law, this probability distribution, which is called as Benford law. Actually, it was introduced for the first time by Newcomb in 1881, but then it was made famous by Benford some years later in 1938, and this is the reason why this law takes his name, but it is actually known also under different names. So under this probability law, the probability of observing a certain digit d can be expressed as the difference between the logarithm of d plus 1 and d, where d obviously takes any value, any discrete value in between 1 and 9. This is an analogous statement of the Benford law as the logarithm of 1 plus 1 over d. So here you have the same figure as before. In blue you have the empirical distribution on the 3 data sets that we are considering. And in red, you have the theoretical distribution under the Benford law. So under the Benford law, we expect to observe as a first leading digit, the number 1, the digit 1, around 30% of times. And we can see that the probability of observing each digit is decreasing as the digit increases. And there is a monotonical decreasing in this probability. The other thing that we can notice is that this theoretical law is approximating quite well the 3 data set, the distribution of the first leading digit in the 3 data set. We have a quite good approximation, quite good quite small discrepancy between the 2 distributions, the empirical one and the theoretical one. And as I told you before, I'm just considering 3 examples of data, but this law is actually applying to plenty of different data sets coming from very different fields. So we've seen populations from countries, but it also applied to other data from populations. So for example, the number of births, the number of deaths, the number of diseases of a certain type reported. But it also applies to data which are very interesting to us, which are financial and economical data. So for example, it has been shown that stock prices comply with the Benford law, or transaction volumes also obey to Benford law, and invoice amounts, expense claims, and so on. So we have plenty of financial and economic data that comply with the Benford law. So how can we use Benford law to fraud detection? We said that many real data obeys Benford law, but actually fake data do not comply with this Benford law. So if we have a set of data which is expected to obey to Benford law, but we observe a large discrepancy between the empirical distribution observed on this data set and the theoretical distribution of the Benford law, this could be due to the fact that data might have been manipulated. So, for example, an overrepresentation or an underrepresentation of a given digit might be a symptom of the fact that data are not real data, but they are fake data. They have been manipulated in some way. And we obviously need some measures of deviation from Benford law, some measures of discrepancy between the empirical distribution, the observed distribution, and the theoretical one. So to introduce these measures of deviations, we will also introduce some mathematical notation. So we will let ND be the observed number of times that digit D appears as first digit in the data set, where obviously D takes values from 1 to 9. We let PD be the corresponding relative frequency, that is the number of occurrences of D above the total number of items in the dataset, of observations in the dataset. And then we let pi d be the theoretical proportion of times that the first digit is D according to the Benford law, so applying the formula that we have just seen. And then we can consider plenty of different measures of non-compliance. So the one that I show you here are just the most commonly used ones, but there are many others. So, for example, we have the chi-square, which is comparing the observed frequencies with the theoretical one, and it's considering the sum of the square distances in some way related to the theoretical frequencies. Or we have, for example, the mean absolute deviation, which consider the distance between the observed proportions and the theoretical one in absolute value, or also the sum of square deviation, which takes the square of this distance. And for all of these statistics, we can determine thresholds over which we can say that the data do not conform with the Benford law. So obviously we are taking the difference between the observed and the theoretical distribution. So large values of these differences determines large values of the chi-square statistic or any other of these statistics. So in general, large values of these statistics imply non-conformity with the Benford law. Benford law has been used plenty of times in detecting fraud. So here I'm just giving you a few successful examples of this. For example, there is a financial advisor, Wesley Rhodes, that was convicted of defrauding investors. And this conviction came from the fact that it was observed that statements that he sent to investors failed to comply with the first digit test. So they did not conform to Benford law. And so a closer examination of these statements revealed that they had actually been faked. So they had been manipulated. Another case, for example, concerned the uncover of a bot network on Twitter, a Russian bot network. And in this case, it was observed that for true Twitter users, the number of followers that their followers have do adhere to Benford law, while for artificial accounts, this does not happen. And so this was a way to uncover false accounts, Twitter accounts, using the Benford law. Another example was to claim that Iranian presidential election in 2009 was rigged, or also it was applied to macroeconomic data. And for example, it was noticed that while macroeconomic data from most of countries do conform to Benford law, in the case of Greece, this did not happen. Macroeconomic data for Greece did not conform to Benford law. And this raised some doubt that Greece could have manipulated its macroeconomic data to be able to join the Eurozone. Other interesting cases, for example, concern the application due to COVID data to discover whether data on death or on the number of people being infected were real or had been manipulated. So how can we use it in the context of tax evasion? We all know that this is a quite relevant problem in Italy. Raffaella just told us this to us before lunch. Just to give you some figures, to give you an idea, in 2021, tax and contribution evasion amounted to something like nearly 84 billion euros. And of these, 73 billion were from lost tax revenues. And the taxes that are more evaded are the IRPEF, followed by value-added tax, IRES, and IRAP. The main instrument, the main tool that the state has to fight firms evasion is that of firms auditing. This is really the only way to see whether a firm evaded taxes or not. The problem is that this is a quite costly, quite expensive operation, and so it would be really, really helpful to have instruments that can be used to target firms auditing. Because the problem is that, for example, in Italy, large firms are much more controlled than small firms. And this is obviously because if we find a large firm to evade taxes, we can gain a lot from this. If we find a small firm evading taxes, the benefit is much smaller. So this is a way to reduce the costs of auditing, but perhaps is not the most efficient way to choose the firm to audit. The large firms are not necessarily those with the highest probability of evasion. And actually, in Italy, is the other way around. It's above all small firms which are evading taxes, even if the amount of taxes evaded is smaller for each of them. So it would be really, really helpful to have something to guide auditing processes. Also, the other problem when checking, when controlling larger firms with a higher probability is that of having some side effects which are not good at all, such as firms deliberately choosing to stay small to avoid a stronger control. So having a better instrument to choose the firms to audit would be really interesting and helpful. So how can we use Benford law? We have the availability of a database, the Bureau van Dijk AIDA database, which contains all financial statements of Italian firms, as well as plenty of other data about the characteristics of the firms. So we might use data from financial statements to see if they comply, they obey to Benford's law, because they are expected to do it if data have not been manipulated. Each statement, at least a statement from industrial, commercial, and service companies, contains something like 243 items, and 163 come from the balance sheet, while the remaining 80 come from the income statement. Unfortunately, we can't use all these items because there are plenty of items that do not apply to certain firms. Some of them are missing values because they do not apply. Some others are identically equal to 0. And then there are also duplicated values because in these line items we also have totals and subtotals. So after cleaning the balance, the financial statement of each firm, we come up with a much smaller quantity of numbers that can be used to verify the compliance, to test the compliance with the Benford law. Here I just show you an example from one firm, one particular firm. This was drawn at random from the population of firms which scored 3 stars on the legality rating released from the Autorità Garante della Concorrenza e del Mercato. This is a legality rating that is asked by firms and released by this authority in case the firm complies to a certain number of legality criteria. For example, the fact of having traceable methods of payments. So let's say that firms with a high legality rating are somehow expected to comply with tax requirements more than other firms in general. And for this firm, for example, we can see that the statistics that we considered all have quite small values. And here in red, you have the the observed proportion for each digit in the sample of data for this firm, and the green interval is a confidence interval according to the Benford law. So if the red points are inside the confidence interval, we don't have any reason to believe that the balance, that the financial statement has been manipulated. This is a different firm. Actually, in this case, we know that there were problems with its financial statements, because it's a firm that has been recently accused of a criminal organization. They were, it belonged to a network of firms that were frauding relationship to the bonus facciate. So we tried to see if the Benford law was able to, I've got 5 minutes.
Yes.
Okay.
Yes.
To see if it worked in this case, if it was able to recognize problems in the statement of this firm. And actually, we obtained larger values of the three statistics, and you can see here a particularly high prevalence of the digit 9. Obviously, these are just two firms. We cannot make statistics with just two observations. The problem is that is the one that you were already underlined before, the lack of label data. So we don't have a sample for which we know whether the firms are evading or not the taxes. So we tried to do what we had. We tried to make a control sample with those firms that are having a 3 stars legality rating, the one that I told you before, and we made also a test sample. This time in the test sample we considered firms with registered offices in Calabria and operating in the economic activity sector of agriculture, forestry, and fishing. The reason why we choose this region and this sector is that this region and this sector were found to have a very high weight of unobserved economy from ISTAT in 2023. So we are expecting in the control sample to have a small proportion or nearly no firms at all with problems in their statements, while we are expecting a larger proportion of firms with perhaps manipulated statements in this test sample. And this is what we got. So in this figure, you have the chi-square statistic for computed on each firm separately for the two samples. And in red, you have the theoretical chi-square distribution. It means the distribution that the data should have if they conform to Benford law. So what we can notice is that in the test sample we have a much larger proportion of firms with very high values of chi-square statistic, meaning firms with a high discrepancy from their observed distribution of the first leading digit and the Benford distribution. For the control sample, this proportion is much smaller. So here is, we did this obviously not just for the chi-square, but also for the other two statistics that we were considering. And here we have, as I told you, the proportion of times the proportion of firms that do not conform to Benford law separately in the two samples. And what we can notice is that we have a significantly high proportion even in the control sample. And this obviously depends on the fact that we are not sure that those firms are all paying taxes. We might have firms evading taxes even in this control sample. Anyway, the proportion of firms not obeying the Benford law is much, much higher in the test sample. And the difference between the proportion in the two samples is statistically significant with respect to all the statistics considered. So to conclude, we have some encouraging results. As I told you, it's still a work in progress. So what I showed you, it's just some preliminary results, but they are somehow encouraging because we found a higher proportion of firms not obeying the Benford law in the test sample than in the control sample. And the problem, obviously, the big problem is that of having a label data. So data which can help us in determining the performance of the Benford law in discriminating between evading firms and non-evading firms. So this is just the bibliography that I cited before. I hope that the statistical audience did not get bored too much because they were very basic things from a statistical point of view, but I had in mind an audience very heterogeneous. So I hope this was fine.